I am Emerson D. Kumlat. In this video, I am going to present the Fourier transform in discrete time signal analysis. We are going to study about discrete time Fourier transform basics and concepts. Later on, we will be discussing some example problems, the step-by-step solutions, and practical applications of this mathematical transformation. Let's begin with the definition. The discrete time Fourier transform, or we abbreviate it as DTFT, is a mathematical transformation used in signal processing and mathematics to analyze and represent discrete time signals and sequences in the frequency domain. It is a continuous function that provides the frequency content of a discrete time signal. The concept is, you can apply DTFT on the signal x of n, but cannot be applied to x of t. It is because x of n is a discrete time signal, wherein x of t is continuous time signal. So we have a signal x of n that is on time domain. If we apply DTFT here, we will get a signal in frequency domain. The notation of the signal is x of omega or x of e raised to j omega. If you are converting a signal in frequency domain to time domain, then we are doing the inverse DTFT. Now we understand the concept. So how we convert? Now we come to the formula to convert time domain signal into frequency domain signal using DTFT. The DTFT is defined for a discrete time signal x of n as follows. X omega is equal to the summation of x of n multiplied by e raised to negative j omega n from n equal to negative infinity to positive infinity, where x of omega is the DTFT of the signal x of n with respect to the continuous frequency variable omega. X of n is the discrete time signal. Omega is a continuous frequency variable. The DTFT maps a discrete time signal x of n into a continuous function x of e raised to j omega in the frequency domain. X of e raised to j omega represents how much of each frequency component is present in the signal x of n. It is a complex valued function, which means it provides information about both the magnitude and the phase of each frequency component. The formula is similar to Z transformation. We knew that x of z is equal to the summation of x of n multiplied by z raised to negative n from n equal to negative infinity to positive infinity. If we substitute z is equal to e raised to j omega, we get the same DTFT formula. That means, if we understand Z transformation, it will be the same as well to DTFT. The graph on the left is a graphical representation of a discrete time function, whereby the graph on the right is a graphical representation of a Fourier transform signal in frequency function. The DTFT maps a discrete time signal x of n into a continuous function x omega in the frequency domain. X omega represents how much of each frequency component is present in the signal x of n. It is a complex valued function, which means it provides information about both the magnitude and phase of each frequency component. These are the basic key points about DTFT. Continuous frequency domain. Unlike the discrete Fourier transform, or DFT, which operates on a finite number of discrete frequencies, the DTFT operates on a continuous range of frequencies. Periodicity. The DTFT is a periodic function with a period of 2 pi, that is x, the quantity of e raised to omega plus 2 pi k, is equal to x e raised to j omega for all integers k. Inversion. The DTFT is invertible, meaning that you can reconstruct the original signal x of n from its DTFT x omega using the inverse DTFT. Complex output. The DTFT results in a complex valued function which contains information about both the magnitude and phase of each frequency component. This can be useful for analyzing and manipulating signals. We do DTFT to find the magnitude and phase of a signal. The signal x of omega can be in polar form or rectangular form. If the signal is in polar form, this is the formula. X of omega is equal to absolute value of x of omega into angle phi. From here, we can get the magnitude and the phase. If the signal is in rectangular form, then we have an additional step to get the magnitude and phase. The formula is x of r omega, the real part, plus j x of I omega, the imaginary part. To find the magnitude, the formula is the square root of x of r squared plus x of I squared. To find the phase phi, the formula will be arctangent of x of I over x of r. If we want to transform a function from the frequency domain back to time domain, the IDTFT is used. So what is IDTFT? The inverse discrete time Fourier transform, or abbreviated as IDTFT, is a mathematical transformation that allows you to recover a discrete time signal from its frequency domain representation, which is usually obtained through the discrete time Fourier transform DTFT, or its discrete counterpart, the discrete Fourier transform DFT. The IDTFT is defined as follows. X of n is equal to 1 over 2 pi, then the integral of x of omega multiplied by e raised to j omega and d omega, where x of n is the original discrete time signal you want to reconstruct. X of omega is the DTFT of the signal in the frequency domain. Omega is a continuous frequency variable, typically ranging from negative pi to pi. Let's have these following examples to understand further the DTFT. Our first example is an exponential sequence. Obtain the DTFT of the signal x of n is equal to alpha raised to the n u of n. As you can see in the sketch, this is a decaying exponential function that starts with 0. The alpha is less than 1 and is a positive number. Based from the formula, we can write the discrete time Fourier transform as the summation of alpha raised to n times u of n times e raised to negative j omega n, from n equal to negative infinity to positive infinity. Use the u of n to reduce the sum from 0 to infinity. Combine alpha and e raised to negative j omega, which are both raised to the nth power. So we can write this expression as the summation of the quantity alpha e raised to negative j omega raised to n from 0 to positive infinity. At this point, we can recall the geometric series formula, which is the summation of beta raised to nth power from 0 to infinity is equal to 1 over 1 minus beta, such that the beta is less than 1. So we will apply this formula to our expression x of omega. We can identify beta as alpha, and that will give us a result of 1 over 1 minus alpha e raised to negative j omega, such that alpha is less than 1. Our second example is a rectangular pulse. Obtain the DTFT of the signal x of n is equal to 1 at absolute value of n is less than or equal to m, and is equal to 0 at absolute value of n is greater than or equal to m. You can see the graphical representation below of the signal. We can take the DTFT using the defining equation, and since we have zeros prior to minus m and after plus m, we can write the sum of 1 times e raised to negative j omega n from minus m to plus m. We arrange the sum into form that we can express in closed form. To do that, we let lower index m be equal to n plus capital M. If we substitute we get the summation of e raised to negative j omega, the quantity of small m minus capital M, from m equal to 0 to capital M. We factor out e raised to j omega capital M. We can then obtain the summation of e raised to negative j omega small m from 0 to 2 capital M times e raised to j omega capital M. To express this sum in closed form, we have to recognize that this expression is actually a finite geometric series. If we have a look on the formula, the sum of a finite geometric series is equal to 1 minus beta raised to L plus 1 all over 1 minus beta, such that beta should not equal to 1. We can express the sum in closed form as 1 minus e raised to negative j omega, quantity 2 capital M plus 1 all over 1 minus e raised to negative j omega, such that omega should not equal to 0. We break up the term e raised to j omega m into a ratio of two terms. This is to manipulate the expression. We will then multiply this ratio to get e raised to j omega, the quantity of 2m plus 1 all over 2, minus e raised to j omega, the quantity 2m plus 1 all over 2, all over e raised to j omega over 2 minus e raised to negative j omega over 2. We divide both numerator and denominator by 2j. Then, we can recognize that this will be a ratio of sine functions from the trigonometric function sine theta is equal to e raised to j theta minus e raised to negative j theta all over 2j. Simplifying, we get x of omega is equal to sine the quantity of w, quantity 2m plus 1 all over 2, all over sine w over 2. You will notice that the numerator oscillates more frequently because it has a larger multiplier. On the sketch, we considering that range from minus pi to pi, and that range the denominator is increasing. The amplitude is 2m plus 1. Let's have our third example on the frequency domain, which is a rectangular spectrum. Obtain the IDT-FT of the rectangular spectrum. X omega is equal to 1 between negative w and 0 outside of that range. The graphical representation is shown below. From the IDT-FT formula, we have 1 over 2 pi, the integral of 1 multiplied by e raised to j omega n d omega from negative w to plus w. And that gives us 1 over 2 pi jn, the quantity e raised to j wn minus e raised to negative j wn. We can express this as a sine function referring from the trigonometric formulas. Our x of n now will be x of n is equal to sine wn all over pi n. Graphing this signal, we have a sine and oscillations. As n increases, the denominator increases and the size of the oscillations will decrease. The zero crossing will be at pi over w. The amplitude is w over pi. Let's have our fourth example on the frequency domain, which is an impulse. Obtain the IDT-FT of the impulse function delta of omega within the interval negative pi to pi. To sketch, we get impulse at 0. Applying the IDT-FT formula, we get 1 over 2 pi, the integral of delta of omega multiplied by e raised to j omega n d omega from negative pi to pi. In impulse, we evaluate omega as 0. That will give us a value of 1 in the integral. Therefore, the x of n will be 1 all over 2 pi. The sketch will be like this at magnitude equal to 1 over 2 pi. This is the tabulated basic discrete time Fourier transform pairs. On the other hand, this is the tabulated basic discrete time Fourier transform pairs for periodic signals. These are some useful Fourier transform pairs for discrete time aperiodic signals. The discrete time Fourier transform (DTFT) has several properties that are useful for analyzing and manipulating signals in the frequency domain. Here are some of the key properties of DTFT: linearity, periodicity, time shifting property, frequency shifting property, time reversal, differentiation in frequency, convolution in time domain, convolution in frequency domain, correlation theorem, modulation theorem, symmetry properties, and Parseval's theorem. These are different properties of discrete time Fourier transform. We will discuss these properties in detail. Linearity property of DTFT. DTFT is a linear operation, meaning it satisfies the superposition principle. It states that if Fourier transform of x sub 1 of n is equal to x sub 1 e raised to j omega and Fourier transform of x sub 2 of n is equal to x sub 2 of e raised to j omega, then Fourier transform of the sum of the weighted signals is equal to their weighted transforms. I repeat, the sum Fourier transform of constant a multiplied by signal x sub 1 and b constant multiplied by signal x sub 2 is equal to the sum of a x sub 1 e raised to j omega and b x sub 2 e raised to j omega. The next property is periodicity. The discrete time Fourier transform x of e raised to j omega is periodic signal in frequency domain with period 2 pi. We can represent the periodicity like this. This is the Fourier transform of the signal x of n, that is equal to x of e raised to j quantity omega plus 2 pi, because the same frequency characteristics repeated after 2 pi period, not only at 2 pi but on 2k pi, where k is any integer. The next property is time shifting property. It is given by this. If Fourier transform x of n is equal to x of e raised to j omega, then Fourier transform of x of n minus k is equal to the e to the power of negative j omega k multiplied by x of e to the power of j omega. If we are going to shift the signal in time domain, then it results in multiplying the frequency domain signal by the exponential term of the delay given k. The same value of k can be multiplied with the transform signal in exponential form. The next property is frequency shifting property. If Fourier transform x of n is equal to x of e raised to j omega, then the Fourier transform of x of n e raised to j omega sub o n is equal to x quantity of e raised to j quantity of omega minus omega sub o. That means, if we are going to shift the signal in frequency domain, it results in multiplying the time domain signal x of n by e raised to j omega sub o n. That is multiplying exponential term of the frequency delay. Omega sub o is the delayed frequency. This frequency shifting property is the dual of the time shifting property. The next property is time reversal property. If Fourier transform x of n is equal to x of e raised to j omega, then the Fourier transform of x of negative n is equal to x of e raised to negative j omega. If we are going to reverse the time domain, the frequency is also getting reversed. Differentiation in frequency. If Fourier transform x of n is equal to x of e raised to j omega, then Fourier transform x of n is equal to j d by d omega of x quantity e raised to j omega. If the time domain signal is multiplied by n, it results in differentiating the frequency domain signal. Convolution in time domain property. If Fourier transform of x sub 1 of n is equal to x sub 1 of e raised to j omega, and Fourier transform x sub 2 of n is equal to x sub 2 of e raised to j omega, then we can state that the convolution of x sub 1 of n and x sub 2 of n results in the multiplication of x sub 1 of e raised to j omega and x sub 2 of e raised to j omega. This property states that the convolution in time domain results in multiplication in frequency domain. Convolution in frequency domain property. This property states that if Fourier transform of x sub 1 of n is equal to x sub 1 of e raised to j omega, and Fourier transform of x sub 2 of n is equal to x sub 2 of e raised to j omega, then Fourier transform of the multiplication of two signals in time domain is equal to the convolution of their frequency. This property is the dual of the convolution property in time domain. This is also called as multiplication property. The next property is the modulation theorem. As we know, modulation is the combination of two signals, one is message and another one is the carrier. This combination mainly used to carry the message signal to a longer distance. That is the concept of modulation. This Fourier transform is also having the same concept of modulation theorem. It states that the Fourier transform of x of n is equal to x of e raised to j omega, then Fourier transform of x of n into cosine omega sub o n is equal to 1/2 the quantity of x e raised to j quantity omega plus omega sub o plus x of e raised to j quantity omega minus omega sub o. The x of n is the actual message of the signal. The cosine omega sub o n is the carrier signal. The resultant frequency domain signal is given by this form. The next property is the correlation theorem. Correlation means it is the relation between two signals, or we can say it is the similarities between two signals x sub 1 of n and x sub 2 of n. If Fourier transform of x sub 1 of n is equal to x sub 1 of e raised to j omega, and Fourier transform of x sub 2 of n is equal to x sub 2 of e raised to j omega, then the correlation theorem states that Fourier transform of correlation between x sub 1 of n and x sub 2 of n is equal to the product of x sub 1 of e raised to j omega and x sub 2 of e raised to negative j omega. For the signal x sub 1 of n, we have to consider frequency x sub 1. For the secondary signal, we have to take the reverse time domain. The next one is the symmetry properties. The Fourier transform of x of e raised to j omega is always a complex function of omega. Omega is the frequency. We can write x of e raised to j omega is equal to real part plus the imaginary part. The real part is represented as x of r e raised to j omega, and the imaginary part is combined with the symbol j, that is j times x of I e raised to j omega. Even symmetry can be represented like this. That is, if we are going to change or reverse the frequency, it is equal to the original frequency range in the transform. So, x sub r e raised to negative j omega is equal to x sub e raised to j omega, because in this real part, cosine value is used. Cosine of negative omega n will yield to cosine omega n. Odd symmetry is the representation of imaginary value of the Fourier transform. We can represent imaginary part of Fourier transform in the reverse frequency is equal to negative x sub I e raised to j omega, because in this imaginary part, sine value is used. Sine of negative omega n will yield to negative sine omega n. The last property is the Parseval's theorem. The Parseval's theorem represents the energy density function of the discrete time domain signal. If Fourier transform of x of n is equal to x of e raised to j omega, then the energy density spectrum is equal to summation of modulus x of n squared from n is equal to n minus infinity to plus infinity. N is equal to 1 over 2 pi the integration of modulus x e raised o j omega squared d omega from negative pi to positive pi. By using this formula, we can get the energy spectrum of the given signal. In summary, these are the DTFT properties. If we talk about DTFT, we have different practical applications such as audio processing, image processing, video processing, feedback and control systems, wireless communications, speech recognition, communication systems in OSI layers 1, 2, and 6. In practice, the DTFT is typically computed numerically using algorithms and is useful for tasks such as spectrum analysis, filtering, and understanding the frequency characteristics of discrete time signals. For practical applications, the discrete Fourier transform, or DFT, is often used instead, as it operates on a finite set of discrete frequencies and can be efficiently calculated using fast algorithms like the fast Fourier transform, or FFT. These are my references. Thank you.